been a great couple of years working with Sanjiban. He's been doing some amazing stuff, getting helicopters to fly, and even today, as we speak, they're actually testing his algorithms. so it's been a real pleasure, and as he was doing this research, I think he stumbled upon some really interesting research ideas on how we can deal with these challenging dynamics and environments and how to plan in those. And so he's going to tell us a lot more. On the phone we have Ashish Kapoor from Microsoft Research and Sid Srinivas from CMU remotely, and Marshall, if they're here. Thanks again, everybody, for coming. In terms of questions, please just ask clarification questions during the talk, and then later we'll have some rounds of questions from the committee, and then we'll open it up to the audience.
Okay. Thanks, Wesley. Good afternoon, everyone. Thanks for coming to my proposal talk on adaptive motion planning. I'd like to thank my committee, my advisor Sebastian, Sid, Marshall, and Ashish for taking time out today to attend this talk. So I'll start with a brief overview of my work. Started here as a master's student in 2011, and since then I've worked on a number of projects that concern motion planning for mobile robots, specifically UAVs. I've grouped my work into 4 sub-themes. So first up, my master's project revolved around motion planning for emergency landing of helicopters after engine failures. This problem was interesting because the dynamics of a helicopter after engine failure is very restrictive, which makes it very difficult to find safe landing trajectories in real time. On the other end of the spectrum, I worked on planning for more agile MAVs for both indoor and outdoors. This presented a different set of challenges, challenges due to fast flight outdoors or due to cluttered environment indoors and learning how to transition between these environments. Thirdly, I worked on some problems related to theoretical limits of flying fast in a forest. So there are some nice links between this problem of forest flight to percolation theory and survival of infinite Markov chains. So we showed that given the density of trees in a forest and the dynamics of a robot, under some assumptions we can bound the maximum speed and the minimum planning resolution for collision-free flight. Finally, my main focus, as Basti mentioned, over the last few years has been motion planning for a full-scale helicopter from takeoff to landing. This problem entails several hard challenges that engulf the previous projects. The dynamics of a helicopter vary widely, from being agile at low speed to restrictive at high speeds, while also being heavily influenced by the presence of wind, pressure, temperature, and cargo weight. The helicopter also operates in all sorts of environments, flying in mountainous terrain to urban canyons. The system must theoretically guarantee safety, even though it senses the world with this limited range sensor. Despite all these debilitating challenges, the helicopter is expected to fly like a pilot. Hence, there's a demand for a high-performance motion planner, and I'll use this application as a running example for my talk. So we first specified at a high level what we mean by motion planning for mobile robots. The objective is to plan a feasible trajectory from start to goal that avoids obstacles such as mountain or no-fly zones. There are 3 main reasons why this is a hard problem. First, the trajectory has to respect the dynamics of a vehicle that the controller for the helicopter can track. Secondly, as the helicopter senses the world with a limited range sensor, it must continually replan to avoid obstacles. Thirdly, since planning must be done on board the robot, it must deal with limited computation. So we explored the following line of argument in today's talk. First, we observed that as mobile robots operate outdoors through changing environments at varying speed, they encounter a wide range of scenarios. We also observed that the performance of planning strategies varies across scenarios. But finally, we advocate for a motion planning system that adapts its planning strategy to maintain consistent performance across the scenarios. So let's take a look at the spectrum of environments in which an autonomous helicopter has to operate, such as trees, mountains, and urban environments. Each environment corresponds to a scenario that favors a particular search strategy. For example, smooth trajectory optimization methods to bend over tree lines, random sampling methods to plan around mountains, or discrete search methods to plan in Manhattan worlds. So what do we mean in this context as an adaptive motion planner? An adaptive motion planning system effectively chooses a search technique by classifying whether a scenario is amenable to a particular strategy or not. For example, consider the search strategy of creating a search graph on the surface of obstacles. An environment with convex obstacles, this is an effective strategy, as the search graph bends around the obstacles. However, on an environment with non-convex obstacles, such as cul-de-sacs, this strategy will result in a large amount of wasted collision checking. An adaptive motion planner in this context will learn a classifier between these two scenarios to decide whether to use a strategy or not. So this thesis proposes that in order for a motion planner to meet the real-time kinodynamic planning performance requirements of a mobile robot, it must adapt its search strategy to the distribution of planning problems that the robot encounters. So this is the outline of today's talk. We will start with the problem formulation for adaptive motion planning. We will present 3 concrete challenges to realize the problem. We will then discuss a framework for running an ensemble of planners to address the first challenge. We will then present a training procedure of automatically generating such ensembles to address the second challenge. To address challenge 3, we will present a training procedure for adaptive planners using imitation learning. Finally, we will conclude with the proposed work. So we start by discussing the problem formulation. We first formalize what we mean by the planning problem. So suppose we have a helicopter that has to plan to a goal point while avoiding obstacles in the world. It has a limited range sensor with which it's detecting these obstacles. In addition, it has to avoid dynamic no-fly zones due to the presence of other aircrafts or generally unsafe volumes. The objective is to plan a trajectory to the goal. The trajectory must satisfy certain dynamic constraints that affect the reachability of the system. So finally, the planning problem is a constraint optimization problem where we're solving for a trajectory, which is a mapping from time to state and control inputs. The objective is to minimize costs, such as the traversal time. The trajectory must satisfy boundary constraints like start and goal. It also must satisfy dynamic equality and inequality constraints. And finally, it must be constrained to pass through a valid free space. We now define what we mean by a distribution over planning problems. So this is a distribution over the dynamic limits and the obstacle configuration that the helicopter is likely to encounter when executing missions at certain speed regimes over different terrains. So for example, on the left-hand side, the distribution that the helicopter encounters when operating at high speed in mountains is very different from the right-hand side, which is a distribution it encounters when operating at low speed near the ground. So we represent the distribution with a finite set of samples, which we call a database of planning problems. This database is created in a very simple fashion. We load a world map where the robot is expected to operate in simulation, sample appropriate start and goal locations, and we append the resulting planning problem into the database. So now we're ready to state the 3 principal challenges, sorted in order of increasing adaptivity to address the adaptive motion planning problem. So the first challenge is as follows. We have a human designer whose role is to design a motion planning system using domain information and knowledge of the planning problem distribution. In this paradigm, we assume that the distribution is fixed. Note that the motion planner in this setup is non-adaptive. But by formalizing the reasoning process that the human designer uses will help us to address the later on challenges. The second challenge examines the paradigm where this distribution can vary after the human designer is done. Therefore, a notion of adaptivity is required. The role of the human designer is to use domain information here to create a library of planners. The challenge requires a meta planner that selects from this library adaptively. So here we use the term black box planners to denote that planners appear to be atomic operations that take as input a planning problem and produce a planning solution. No amount of intervention or inference is allowed in this paradigm while the planner is computing. Hence, this paradigm allows the designer a lot of flexibility to create any sort of black box that attempts to solve the problem. And the meta planner can work with these black boxes. However, the downside of the black box planner paradigm is that it's computationally inefficient. So a lot of time is spent extracting context from the planning problems, then making a selection before planning can even begin. In addition, the meta planner can't intervene once it has made a choice. Instead, we consider the white box paradigm, where the search strategy itself adapts during the planning cycle. This is resource efficient because decision-making and inference about the world is interlinked. This leads to challenge 3, where not only is the distribution varying, but we are interested in computational efficiency. The role of the human designer in this case is to design a white box planner with a tunable policy that affects search. And the goal of this challenge is then to train this policy to maximize effectiveness on a distribution of planning problems. So we briefly touch upon some categories of related work and the intersection in which this thesis resides. The first category engulfs methods where planning problems are modified to exploit planning problem structure, such as adapting search techniques, using local trajectory optimization techniques, or even hybrid searches. The second category of methods are addressing non-holonomic motion planning. There are methods, so the categories are methods that address the hardness of the problem, provide methods that provide semi-analytic solutions in obstacle-free environments, methods that compute approximate solution using state lattice searches, or full-fledged kinodynamic planning methods by randomly sampling the control input space. The third category are methods addressing machine learning techniques applied to motion planning, such as learning to predict trajectory optimization seeds, learning to divide the C space and apply different techniques, learning heuristics, or even learning policies for planning. Our work lies in the intersection of these methods. We'll now present a framework that runs an ensemble of diverse planners to address challenge 1. So challenge 1 requires a human designer to design a motion planning system using domain information and knowledge of the planning problem distribution. So let's begin by addressing the issue of solving a planning problem. So recall that this is a high-dimension constraint optimization problem that needs to be solved in real time. We achieve this by using the following expert planner framework. This framework decouples the problem as follows. Firstly, a surrogate low-dimension path planning problem is framed. Secondly, a planning algorithm is invoked to solve this planning problem. Finally, a velocity profile is solved for, and a nonlinear filtering technique is applied to project the path into feasible trajectory space. The word expert is used to denote that each module in this framework must be carefully selected. However, the planning algorithm module allows for a fair deal of flexibility. So it can be decomposed into 2 steps. First, an implicit graph is created by placing vertices and defining connectivity rules. Secondly, a search method is applied on this graph to compute a path from start to goal. And the flexibility really lies in the choice of this implicit graph. Different graphs are suited for different planning problems. For example, one can randomly sample states or uniformly place vertices to create low dispersion graphs. One can even create custom graphs by exploiting domain knowledge and placing vertices and edges in areas likely to have a solution. So we've explored this avenue of custom implicit graphs that exploit planning problem nature in several domains. For example, on the left-hand side, on problems with narrow passages, we have used graphs with locally optimized edges to bend through the gaps. In the center, on problems with obstacle clusters, we came up with sparse visibility graphs that sort of bend around obstacles. Finally, on problems with very restrictive dynamics, we have used graphs with reachability-informed nearest neighbor functions to speed up planning. So we now return back to the problem of designing an expert planner for a distribution of planning problems. It's unlikely that one expert planner will meet the performance requirements on this entire distribution. And so one candidate framework might be to hand design a decision tree that encodes the logic of deciding which planner to invoke. While this is computationally efficient as all resources are assigned to a single planner, there is an inherent difficulty in accurately predicting planner performance. To understand this issue, let's look at an example. Say we have 2 planners. Planner 1 focuses its search in a volume, shown in blue, and as a result is able to find the solution that passes through this gap, shown in green. Say we have another planner 2 which does not focus its search and is not able to find such a good solution, shown in orange. Now on the right hand side, a small shift in one of the obstacles makes it impossible to find a solution through the gap, rendering planner 1 ineffective, while planner 2 still finds a solution. It would be very difficult to hand code a logic to detect this event. Hence we advocate for, instead of a single planner, running an ensemble of planners in parallel and taking an argmin over the solutions. So in this framework, we want to run diverse planners with complementary strengths, such as at least one of them succeeds in solving the problem. Since all the planners are not expected to solve all the problems, we don't need to accurately predict performance. Diversity of the ensemble is key. We note that adding a planner to an ensemble has a monotone submodular benefit that allows greedy ensemble construction algorithms to have guarantees. And we exploit this to create an ensemble creation algorithm as follows. We collect a database of planning problems and design a planner to solve most of these problems. That's shown in line number 4. We then prune out all planning problems that this planner solves, as shown in line number 6, and we repeat this process. And due to the monotone submodular property, this algorithm has a guarantee of solving at least 63% of the problems that an optimal ensemble would have solved. So we now show some results for creating an ensemble for an autonomous helicopter. So shown here are 2 planning problem distributions that we conducted tests in. On the left, we show missions done in West Virginia where the terrain was such that obstacles of interest are trees, towers, and no-fly zones. On the right, we show missions in Arizona where the terrain had mountains and hills. So let's take a look at the first distribution. So both expert planners, we ended up designing in the ensemble here, Chomp 1 and Chomp 2. They're local trajectory optimizers. Chomp 1 is a planner which initializes itself using a visibility graph technique and uses a covariant gradient descent to improve the trajectory. This planner was able to solve most of the problems due to the presence of good local minima. However, we found that this planner had some problems when going over tree lines because vertical avoidance was preferred without any sort of lateral deviation. So a natural fix to this was to make another planner, Chomp 2, that projects the gradient into the z-plane. And together, this combination was able to solve all the problems that we encountered. Now contrast this to a different planning problem that we encountered when doing flight tests in Arizona. So the ensemble in this case is different. While the first planner still remains the same because Chomp 1 can smoothly bend trajectories around mountains as shown, we encountered cases where it would get stuck between a mountain and a no-fly zone because of bad local minimas. So this led to designing a second planner, which we call RT star tunnel 1, which is essentially a random sampling method that focuses sampling in a particular search volume to power through these gaps. And hence it's able to solve problems where Chomp 1 gets stuck. So in addition, we evaluated the ensemble on a variety of datasets in simulation by creating different worlds. So the first dataset is a world with only towers in it. The second one is a world with only walls in it. Then we have more realistic datasets like doing simulated missions in Grand Canyon or simulated missions in our urban city environment. And in all of these cases, we found that just adding a second or third planner was able to solve all of the remaining problems. So we'll now present a training procedure for meta planners to automatically select ensembles to address challenge 2. So to recap, in this paradigm, the human creates a library of black box planners. Then as a planning problem distribution changes for different missions, a meta planner is expected to select an ensemble from the library. Now we can have 2 kinds of meta planners. One that's making a static selection and one that's making a dynamic selection which varies with context and time. So today we'll be talking about the dynamic selection. And the question we're interested in is how can we train such a meta planner? So the problem formulation is described as follows. We have a planning problem from which context is extracted, such as probing an occupancy map at various locations. We have a library of planners, and we want to train a meta planner phi that maps a planning problem to an ensemble such that the cost of the best planner in this ensemble is minimized. The way we predict an ensemble is by having a list of predictors, each predictor predicting a planner for a particular slot. So here we have pi1, pi2, pi3 that predicts planners p1, p2, and p3 in the ensemble. We need a training rule to train these predictors. So we first examine the training procedure for a single predictor. On examining the problem, we find it's a loss-sensitive classification problem, which essentially means that the penalty of misclassification is the difference in cost of a selected planner and the best planner in a library on that planning problem. So let's take an example to see what are the implications of such a loss function. Say we have 3 planning problems, gamma 1, gamma 2, gamma 3, and we have 3 planners in the library, P1, P2, P3. Now, the best planner is shown in green. Now, for problems 1 and 2, there is a clear distinction between the best planner and the remaining planners. But for problem 3, roughly all of them does the same. So it's clear that the classifier should do a better job of solving problems 1 and 2 rather than 3. And that's essentially what the loss function says. So now when you introduce a second predictor, the loss function simply states that terms where it can do better than predictor 1 are the terms that matter. So we illustrate this as follows. The planning problem dataset can be categorized into 2 categories. Green, which are problems solved by predictor 1, and red, which are problems that are unsolved by predictor 1. This simply means whether the loss-sensitive classification error was low or not. And the loss function states that the problems in red are the ones that matter for predictor 2. So we exploit this property by proposing to train a list of predictors by greedily stacking loss-sensitive classifiers on top of each other. Hence, the deeper predictors in the list focus on unsolved problems by its predecessors. In other words, they learn to solve the harder problems. Greedily training a list of predictors has been examined by Day et al. They show in their Consequent algorithm that greedily training such predictors have near optimality guarantees due to Morton's homogeneous property of the loss function. In our work, we have been focusing on how you train such loss-sensitive classification problems using convex surrogates such as hinge or square loss. So we now present evaluation of this method on a spectrum of planning problems. First up, we are looking at predicting an ensemble of trajectory optimizers that use different seed trajectories to initialize themselves. And then the initial trajectory is optimized using a Chomp algorithm. So we evaluate on 2 datasets. First is a trajectory optimization of a 2D point robot, and secondly, trajectory optimization of a 7D manipulator. In both datasets, we see a dramatic reduction of loss when predicting 3 elements as opposed to predicting a single element. So next up, we look at predicting different heuristic-based planners for 4D on planning. These heuristics are used to guide a 4D search while minimizing the number of expansions. And the final dataset we tried it on is predicting an ensemble of 2D motion planners. And in all of these cases, predicting an ensemble does far better than predicting a single element. To get some intuition behind what's going on, we show that deeper predictors learn to solve harder problems. So let's do an analysis of the 2D trajectory optimization problem. So you see that the level 1 predictors learn to solve the easy problems, like going left or right of obstacles, while the level 3 predictors focus on the harder problems, the corner cases, where it predicts trajectories going through narrow gaps surrounded by bad local minimums. We also see the same artifact for heuristic datasets for 4D arm planning. So here the arm has to bend from start to goal while avoiding obstacles. Here heuristics are configurations that attract the search. Imagine them to be tucking configurations that the search prefers. So level 1 naively predicts a tucking configuration that's pointed towards the goal, but it gets stuck because of the block on the upper part of the planning problem, while level 3 predicts this non-trivial tucking configuration that powers through the gap. Finally, we evaluate our approach on a dataset we care about, that is full-scale helicopters. Here, the planning problems are created by sampling no-fly zones from a particular distribution. And we see that the meta-planner that predicts an ensemble does better than predicting a single planner. So we will now present a training procedure for adaptive planners using imitation learning techniques to address challenge number 3. So to recap, we saw that the black box paradigm wasted time extracting context and then selecting which planner to run. On the other hand, a white box paradigm that can interleave decision and inference can be computationally efficient. So in this paradigm, the role of the human is simply to make a white box planner. imagine that to be a planner with a tunable policy. The role of the policy is to make decisions that affect planning, and the policy will observe some outcomes and infer details about the problem. And we are interested in how to train such policies. So we start by gathering some intuition by examining the problem of learning a heuristic policy to guide search. Say you have a distribution of planning problems which corresponds to these worlds where obstacles are shown in red. Some of these problems have a cul-de-sac which act as traps for aggressive search. So say we sample a problem from this distribution, and our goal is to learn a policy that guides a search tree from start to goal. Note that this policy is not allowed to explicitly extract any sort of context from the environment. It can only infer properties based on outcomes of collision checking. So formally, we want to learn a policy pi that maps the state of the search, psi of t, into a decision, a of t. So, for example, the input to the policy here is the search tree, which is nothing but the history of decisions done and outcomes observed. The output of the policy is a set of candidate edges that can be expanded. And on making a decision, the policy observes an outcome, whether the expansion was successful or not, or whether the edge was in collision, as is the case here. And this allows the policy to make an inference. In this case, rule out all worlds. In this case, realize that because the middle two edges are in collision, there's probably a cul-de-sac in the middle. And having made this inference, the policy guides the search along the sides till the solution is found. Now, training such a policy falls into the realm of sequential decision-making under uncertainty. The key aspects of the problem are as follows. The output of a policy at any time step affects the input to the policy in the future. And the utility of a decision can only be obtained at the end of the planning cycle when we evaluate the cost of the trajectory. So when we look at the training optimization for this policy, we see two main artifacts. Firstly, the distribution of search trees is non-IID due to its dependence on the policy pi. Secondly, the loss function Q also depends on the policy. So these two facts imply that the problem is no longer in the supervised learning domain. So we can't simply train it. So we propose a solution to use a combination of imitation and interactive learning techniques to bring it back into the supervised learning domain. Firstly, we changed the lost function from qpi to qpi-or, which essentially signals that we want to imitate an oracle. So the term clairvoyant oracle here is used to denote that this oracle can fully process the planning problem at train time and find a good sequence of actions. Hence, imitating this oracle is a desirable objective. The second thing we see that we circumvent the non-ID distribution issue using interactive learning, where we train a policy, use it to collect data, aggregate the data, and retrain the policy and so on. Using analysis similar to Ross and Bagnell, we show that such a training procedure leads to nice performance guarantees. We applied this idea in the domain of informative path planning. The objective here was to learn a policy that, given the current knowledge about the world, chooses a location to visit to gain the most information. As one can see, this domain shares a lot of similar properties to sequential decision-making under uncertainty, similar to the adaptive planner problem. So the algorithm we came up, Explore, is able to learn custom information gathering policies. For example, if we train it on a dataset of ladders, it learns that spiral motions result in good coverage of the ladder. Training a dataset of warehouses, it learns making large sweeping motions is good for covering warehouses. We evaluated this Explore algorithm on various datasets and observed that it was able to learn custom policies for these distributions. As we can see from the plots, the green bar, which is the Explore algorithm, competes with the best hand-selected policy on both datasets. We also tested it in a realistic 3D office desk scenario where we trained on synthetic data and tested on real data. And the video shows that the algorithm is able to generalize pretty well. Okay, so finally we'll now talk about the proposed work. So I propose to develop a fully functioning adaptive motion planner and demonstrate it on the autonomous helicopter platform. The proposed work can be categorized into three main groups. Each group maps to different research questions. Answering them would provide some of the missing pieces for an effective adaptive motion planning framework. Firstly, white box adaptive planners. We saw that they're computationally efficient as the search strategy itself adapts. So we propose to learn different kinds of planner policies using approaches that we discussed to address challenge 3. The second is black box adaptive planners. So we mentioned that the black box paradigm was attractive because it allowed the user a lot of flexibility to design any sort of system to solve, any sort of black box to solve these motion planning problems. However, these methods are really dependent on context extraction, and we propose to see how we can alleviate such issues. Finally, we deal with issues that are likely to arise when this system is running online and you have train and test mismatch. And we suggest some online strategies to deal with that. So let's start with questions related to the white box adaptive plans. The first question we look at is how can we efficiently train a heuristic policy that guides an underlying search method. So we briefly discussed this during challenge 3, but we take a closer look at the kind of behavior we expect. So let's say our planning problem distribution contained a bug trap or a cul-de-sac which trapped aggressive search process. So the kind of behavior we expect from our policy is that after realizing some of the cells are occupied, this policy switches to guiding the search along the outer flanks of the planning problem. However, if we change the distribution of planning problems into worlds where such bug traps don't exist, we expect the policy to aggressively search towards the goal. The question is, how do we learn such behaviors? We want to approach this sequential decision-making under uncertainty problem in the framework of imitation learning, as we discussed. Here, policy to imitate might be Dijkstra at train time, and we hypothesize that such a training procedure would result in an effective policy that customizes its behavior on the planning problem distribution on which it's trained. Okay, so the second question that we tackle, even in the white box paradigm, is learning a collision checking policy. So the issue with a heuristic policy is that it's restricted to check a set of edges that can result in progress of the search. However, as often is the case, edges outside of this set can be more informative. So let's take a look at a following example. Say we have a database of worlds where we have a wall with a narrow passage. This passage has a gap either at the top or the bottom. In such a case, if we check an edge that disambiguates between these two worlds, it can be very informative. For example, here knowing that there is no gap at the bottom, we can now check a sparse set of edges to find a path that's probably collision-free. So we approach this problem through the framework of Bayesian active learning. To illustrate what I mean, say we have a database of planning problems, which we call candidate hypothesis. At test time, we assume the world belongs to one of these planning problems. So one of the hypotheses is true. We can group these problems into regions or clusters such that one path is feasible. So, for example, in all these worlds, path 1 is feasible. In all these worlds, path 2 is feasible, and here path 3 is feasible. Now, checking an edge for collision serves as a test. So, depending on the outcome, we can prune out worlds that are inconsistent with this outcome. So, if this edge is in collision, we can remove all the worlds as shown. Even if an edge is free, we can remove inconsistent worlds. And the goal is to drive all uncertainty into one region, which would correspond to finding a feasible path. And we want to do this while minimizing collision checking effort. So this problem is generally known as the decision region determination problem, and efficient greedy algorithms have been provided by Choudhury et al. We hypothesized that solving this decision region determination problem would result in an efficient collision checking policy. So we now move to resolving some of the shortcomings which we saw in the black box system. So let's revisit the paradigm where we extract context from the planning problem, and a meta planner uses this to select a planner. Now, observe that the context extraction needs to capture a lot of high-resolution information about the problem to decide whether a planning strategy is effective or not. And this can be computationally wasteful and lead to high-dimensional feature spaces. However, we can leverage one fact that the planning problems and successive time steps are tightly coupled because the helicopter doesn't magically teleport from one time step to another. And so using the performance of a planner in one time step as a strong information signal for determining which planners to use and the next time step might be effective. To take a look at what this means, say at time step T, planner A, which focuses its search in a certain region, fails. We can use this to select another planner that focuses in a different region, and condition on these two failing, we can make a more informed decision at time step T plus 2. Now, interestingly, if the planner performance is used as part of the context, it's no longer effective to just do exploitation. That is, at every time step, picking the best planner. A certain amount of exploration is needed. Selecting planners whose outcome can help determine future decisions. So we hypothesize that efficiently balanced finding an exploration-exploitation strategy will lead to an effective meta planner. So finally, we talk about dealing with online failure cases. So let's take a look at what we mean by failure. So if at any point of time, the planner is unable to solve a scenario, that is, it sees the next scenario at the next time step. So this repeats till the system is forced to execute a safety maneuver. At that point of time, maybe a human has to intervene, or maybe an offline planner has to be invoked to rescue the system. Our goal is to encounter such safety maneuvers as infrequently as possible. Basically, even if this were to happen once during a mission, the system should not repeat the same mistake again. Formal explanation for the problem is training and test mismatch. The particular failure case might have been a rare event in the training dataset. However, in the online case, failure implies the robot sees the same problem at the next time step and so on. So to deal with this distribution mismatch, we resort to online learning methods that make little assumption about the distribution. So we propose an online learning framework where the system uses an algorithm to select from a library of exception planners. We'll elaborate later on what we mean by exception planners, but for now, think of them as a lookup table that records past failure events and expected solutions. This library will be dynamically updated on the fly, and we need an online algorithm that can select from this library. So this leads to two interesting questions. The first question is, how do we select expert planners in an online fashion? So this can be framed as a multi-arm bandit problem where selection is made and feedback is received. However, because the library is dynamically changing, the conventional regret formulation does not hold. And there is some work on the framework of sleeping bandits to deal with this problem, where the set of experts dynamically change over time. The second question we deal with is how can we create exception planners on the fly? So ideally we want a data-driven approach that looks at the past failure cases and produces a solution to solve these cases. While in general this is a hard problem, we hypothesize that failure cases are likely to be spatially similar. This basically means that they're likely to be these pathological conditions that we haven't modeled when we made the planning problem datasets. And if this hypothesis is true, a way to create planners would simply to derive search volumes to focus the search. So these are very similar to ideas in the past based on caching good solutions in extended RT or using experience graphs to speed up solutions. Finally, in addition to answering some research questions, we are interested in producing and releasing open source code and datasets. Specifically, we're interested in releasing in two kinds of datasets. One for interpretation purposes of how adaptive planners behave, and more realistic datasets for autonomous helicopters to evaluate the effect of various planning frameworks. So to summarize today's talk, we formulated adaptive motion planning in terms of three challenges. We argued for executing an ensemble of diverse planners to address challenge one. We showed how to train a list of predictors to adaptively select this ensemble to address challenge 2. And we presented an approach to train an informative planning policy using imitation learning to address challenge 3. In our proposed work, we wish to design white box adaptive planners by exploring learning heuristic and collision checking policies. Additionally, we want to improve our black box planning framework by using planner performance as feedback. Finally, we want to explore techniques to deal with failure during online execution. This is a timeline for my proposed work. I aim to explore the white box planning strategies first and look to publish the results by May of next year before moving on to exception planners and improving the black box planning framework. Aim to defend sometime this next year. And so finally, rounding up today's talk, the take-home message is that as a mobile robot navigates through various scenarios, an adaptive motion planner is vital to ensure consistent performance across these scenarios. Thank
you. We will start with some questions from the remote members.
Yeah.
Very nice talks. All of you on the hard work.
Thank you.
I have one question regarding your work on the second optimization. Would you tell us how big are your sets that you are optimizing over? Like, what's the size of the sets of planners?
So typically the ensemble size is something from 2 to 3 or 4 maybe, depending on how much computational budget we have. The libraries, for the tests that I've shown results for, they have been ranging up to 22, but in theory they could be much larger.
Okay. This is my only question really was that if it's small, your set is small, then why not just do exhaustive search as opposed to go to the some other greedy optimization?
Yeah, you mean all brute force combination of all three planners?
Yes.
I see. So I think because of the diminishing returns, I don't think there will be a large gain. And I mean the attractive part of the greedy method is that if this set were to go a little bit larger, it would be even if it were to go to 5 or 6, it will still be efficient to compute. And it also, another important thing is it also leaves the door open for online methods. If there was a reason to use this method online, that this exhaustive search would become very difficult, while the greedy list of predicting policies they have nice online update routes. So for that reason, I kept it. I kept the training procedure.
Okay, yeah, definitely. When your size of the set grows bigger, it makes sense. So I'll let other folks ask questions.
Is it me?
Yes.
Great. First of all, thank you for the wonderful talk. I really enjoyed it. And I've been working with you on some of these things, so I'll spare the specific technical questions for our meeting.
Sure.
More high-level couple of questions. One is, you rightly point out that the performance of a planner depends quite significantly on the environment that you're planning in.
Mm-hmm.
Because fundamentally, every planner is sort of within its heart making some assumption about what its environment looks like and what it's good at in that environment. So one question for you is, if that is truly the case, would it make sense then to learn more about the environment first, rather than learn how to solve the planning problem? So there's this sort of exploitation trade-off, right? Like you can spend some samples and explore your environment, build, for example, a blue space model in configuration space, or build some prediction on what the world might look like, even before you start answering any queries.
So I guess if you had some reason to believe that the world that specific planning problem would remain constant across planning cycles, I definitely think that's a good way to go. So, for example, I guess, for a mobile robot operating in a fixed environment, like a kitchen, I guess, that would make sense to understand some properties of that static world. I don't make assumptions about like that in the work I'm suggesting. So in that case, if you're thinking of, if you're saying, well, given a planning problem, should I spend some time exploring first and then exploiting? Really, your task loss is ultimately how good you do at the end of the planning cycle. Right? So if you're learning a policy, the training rule must care about that task loss, not so much about how much information you've gathered about the world. So right, so it depends on the paradigm is, I guess, what my answer is. I think for cases where we believe there's something fundamentally common across all planning problems, and condition on that assumption, we should. It'll be advantageous to create a belief model and then exploit that model on the fly. But where that assumption doesn't hold, if you just get a brand new problem and you're spending some time understanding what your planning problem is, you need to explore the part that's useful, I think. So that's why the task loss should be the loss you care about.
So another question is, oftentimes you are willing to trade off path quality or solution quality for planning time. And so you may choose a far more suboptimal solution initially because you know you can get that solution quickly. How do you incorporate that sort of trade-off in your paradigm?
So it's a little tricky because you would have to determine the utility of getting a solution earlier on. It might be that if you get a bad solution earlier on, you want to start following it while you replan. Is that the paradigm you mean, where you get a poor solution earlier and you start following it while you're improving it?
So there's sort of two ways to do it, right? One is to do it real time, like what you're talking about, where you start following your suboptimal solution first and improve it over time. The other is to do it anytime, which is find the suboptimal solution, branch and bound, before your robot starts moving and then you get a time cutoff from your operator saying, look, I gotta go now.
Okay.
And I think they're both fairly valid paradigms.
So
oftentimes, I guess we're driven by time more often than we're driven by solution quality.
Sure. I guess in the way I set up the framework, it doesn't really reward you for coming up with those interim paths. It only matters what is the final path you came up with at the end of the time budget. So I would have to think about how the loss function has to be changed to reward that. Maybe it's the it can be the loss function somehow has to capture this anytime nature. So
when you're thinking about it for like 15 minutes during your talk, I could figure it out. But I think it's definitely a thought that came to my mind. And then finally, quite long. One thought, and people have thought about this in the past, is to learn heuristics that guide search over the sort of high level, like two-choice planners.
Yes.
And of course, you know a lot about this, about learning heuristics. What do you think of that paradigm? Essentially saying that, look, there is going to be a search, the search is critical, but the focus is more on guiding the search rather than picking which planner.
Yeah, I think most of the related work on heuristic search is exactly that. Ultimately the loss function that the loss function they use is not the loss function we care about, which is how good was how much search effort was explicitly reduced, right? It's more about, well, can I learn a consistent heuristic, or what's the probability that the heuristic would predict the optimal path? But say, for example, to take your point, say I'm trying to train a heuristic to predict whether a state belongs to an optimal path, and I incur an epsilon error in that prediction. Now that might mean a really, in terms of search effort, that might really throw me off, that epsilon error, right?
Yeah.
On the other hand, if I have another policy which doesn't do such a good job of saying which state belongs, but it can roughly distinguish between really bad rabbit holes and guiding the search in the right area, I would prefer that kind of a heuristic, right? Because that would have overall loss. And I think some of the related work misses out on these on the correct loss function to be used. So I think that's what I'm interested in exploring. Learning bad heuristics which are still very good for search, I guess.
Cool. Thank you.
Yeah.
So, very good work, I think. Fantastic presentation. Coming back to this question of exploration, what is assumed what is assumed known of the environment?
What is assumed known?
Of the environment.
Of the environment. Oh, so the planning problem. Essentially, each planning problem has full access to, like, it's like an occupancy map that you. So the way I deal with it is that a planning problem is you know everything about the environment because it goes in a receding horizon fashion. So you don't have to. So you know everything within that horizon. I don't reason about what is in the unknown space and an effect of, because we make optimistic assumptions about the unknown. So that I've not dealt with. Just dealt with, okay, if you've decided to make an optimistic assumption about unknown and just plan up to a horizon, how can I do that better? So
coming back to this exploration part that you were asking about, it seems like in many cases by making a small additional step to get a little bit more information, you can get a few numbers reward the efficiency of the path. And maybe that can become now. Your answer had to do with exploring complete environment, the example you gave.
yeah,
So of course that's not useful in this kind of
yeah.
However, what might be useful is to run policies that tell you if this is my partial view of the environment, by taking this small additional step, you complete, for example,
I see.
that kind of thing.
Yes, definitely.
So is that something that
Yeah, definitely. In fact, even though I don't explicitly address it, I think the kind of work I was proposing for dealing with these adaptive planners, some of this, the philosophy carries over. It's still they're under sequential decision making, right? You still want to explore first, and then and learn a policy, learn something
That's
about
what
it.
I'm talking about, right?
Okay.
Well, if you do that purely sequentially, then that's very
Okay.
limited.
Okay.
But maybe there's a way to have minimal,
I see.
minimal additional step.
Okay, I see.
So it costs you very little to high reward.
Okay, I see. Yeah, that would be interesting. Yeah. Okay.
So actually, my question was a little on the metrics or how you quantify performance, right? Like you say like high performance or something like this, and there's some when you do this planning, you add some overhead on top, right? So it's not just expansion, right? It's like that additional part plus research algorithm, right? So how do you quantify performance?
I mean, essentially, what I mean by performance is whatever this solution comes out to be, there is a mapping between a solution to a scalar number. Every planner is given a time budget, and in that time budget, if it couldn't find a solution, that's a very high number. And then, so all the comments I'm making about performance are what is the expected value of this metric.
So you have a fixed like block time budget.
Yeah. So I did this to tame the problem. Otherwise, there are some planners which don't satisfy constraints, but when they do, they come with a solution. So it's hard to deal with those factors. So I simplified it by just saying mapping everything to a scalar number, and then you can bring in machine learning techniques because now you have a loss function.
Okay, so you're basically saying you have a fixed time budget and whatever is the best cost.
Sure. Yeah.
And then one other question I had is, so for some planners, there's some temporal component where like you reuse information, like T-star,
Sure.
you reuse some tree from
Yeah.
T-star. Is there a way to
Interesting question. Those are some of the actually that's along some of the lines which Sid was what I was thinking about with Sid's question, which was right now I assume that the memory is clear, and so the memory starts here and ends here, and that helps you decouple decision making across time steps. If that were to be involved, you would have to factor that in. It's not that it's not completely impossible to think about it, because I feel just pull up. So in this paradigm, when I'm using the performance as a feedback, I think we are naturally tying in the temporal component into it, and so there might be a possibility to push it into this framework to say, well, I use this planner at this time step, and conditioned on that fact, maybe the performance will be better the next time step. But the other comment is why I haven't pursued that line of research is that because the vehicle is moving very fast, it sees so much new environment that reusing search trees is up to a point of time is no longer effective. It's more work to reuse it. And, in practice, it just is cleaner to just start from scratch. And so that's why I've been explicitly interested.
Have you explored trying to solve a single line problem, breaking it into chunks and using ensembles?
Yeah, so there's a lot of related work on from Nancy Amato's group. She started it, and then there's a group in Texas, and they've done a lot of work where they decide how to split up the C space and then apply different techniques. I think that makes sense for these really large problems, like the piano mover problem, for example. It's not particularly useful for the kind of problems I'm looking at, because stitching together, because if you split up the C space, where do you plan to and how do you stitch it up is not trivial. So unless you can define sub-goals that you have to go to, it's not the easiest thing. So I haven't looked at, but there's a lot of work.
Have you thought about case-based reasoning to improve what planner you select? So if you already shortlist from your planning problem database the types of environments that your planner is kind of reaching or seeing, and you already know that in these particular scenarios from past history, a majority of the world might be, say, Manhattan-ish kind of feel, and then it goes into more of a forest, central park-ish kind of feel. And so then your case-based reasoning would say, well, given this kind of environment, we generally select this planner followed by this planner, making it a little faster for you to replan around the environment.
And that's a really good question. And that's where we started from, where we were looking at really simple planning problem distributions where we said, oh, well, if it's here, we should use it. It's like a good if-else tree. What happens is as you make these, as the demand for performance increases, these distributions are no longer such bimodal, they become much more complicated, and that tree starts exploding. Like it's no longer Manhattan, but it's more about obstacles in particular configurations can upset the plan. Because to get planning, to meet the performance requirements, these planners have to really make strong assumptions about the world, and so they're very brittle. Small changes in the obstacle environment can upset their performances, and so that's what motivated this line of doing this automatically instead of case-based reasoning. There's too many cases.
So, just a follow-up. So then could you maybe shortlist the kind of sampling that you're doing of the problem database by using something like an e-graph or demonstration-based data to start with, and then replanning and continuing from there? I mean, I'm just trying to figure out how to reduce the plan.
You mean how to reduce the number of... I see. I think the other motivation is we do want to go towards a framework where we're not doing this as much manually, because it's not so much about one system and making it work. We're talking about a framework, and while that might be interesting, I think having an automatic way to do that would be better. So, I guess to translate what you're saying, having more interesting context extraction method that sort of captures that would be a way to follow.
Maybe we can go back to the committee. Do you have some more questions?
Just to, I guess, asking question. So a lot of parents and grandfathers still work on ensemble and machine learning, ensemble classifier, and there is a notion of weak classifier there. So classifier needs to attain certain level of performance in order to work well in ensemble. And is there a notion that you can think of that might be applicable here in terms of performance of these planners, or just so that maybe there might be a possibility of building some
Yeah. So for example, So I think the difference is so for example, if you take boosting for example, and you have a lot of weak classifiers that you're stacking together to really create a powerful classifiers. I think that would be something which Sebastian was asking along. Like if I have a planner that's reusing previous search to sort of incrementally become better and better at solving a problem. So that's a very interesting line. It's just I haven't kind of explored that domain because mainly been exploring one planner trying to solve one problem. Because a weak planner on its own can't solve the problem, but maybe a second weak planner can improve it. I think that's like an interesting parallel, basically some sort of a chaining of planners and what we can what can be obtained from that. But I haven't really looked into that yet.
Thank you.
Can I ask a quick question? Sure. So, from what I understood, the features you use to choose your optimal planner, let's say, are based on collisions. Do you plan, when you think of a real environment where you're flying a helicopter, you have usually finite scales. So let's say trees, buildings, mountains. And have you planned on perhaps using other features, such as visual features, to also help you plan?
Yeah, I sort of sidestepped context. I think it's a big important issue. I so far the context I've used for are purely geometric, just because I think to understand if you keep it geometric, you're sort of being fair. You're not using other information. You're just using the information a normal planner would have used. Things like other modes of information are a normal planner would not be able to use it, and so that's unfair to compare. But there definitely, I think, for example, semantics for mobile robots, I think that's extremely important. Knowing that I should not search underneath a tree or underneath the ground. We have examples where we waste a lot of time searching these spaces which are completely ridiculous. We know from data an optimal solution would never lie. So if you were to use this information in the context itself, statistically the methods should just follow through the framework, and you should be able to know that these problems that I was talking about. It's an interesting one.
Sid, do you have any more questions?
One,